This is Jack from the PyTorch XLA team at Google. Today, I want to talk about the PyTorch XLA SPMD, which is the new technology we use to do the distributed chaining. So the agenda item for today, I will briefly talk about what is GSPMD, go over the mesh and partition spec, which are the core concept between the GSPMD, go over some graph for the basic idea, and then quickly go over a Colab example. So let's go. So what is GSPMD? You can probably read this paper, which is published in 2021, I believe, by Google. So the GSPMD is standing for, I don't know what G is standing for. SPMD is standing for the single program multiple data, which means you only compile a single program, but the data is different on different device. So the core idea between the GSPMD is that in the distributed chaining, users don't need to manually inject collective ops like or reduce scatter. User can only express the sharding intention, like I want to shard this tensor at dimension 0 by 4, and then compiler will convert those sharding intention into actual collective, and it's going to propagate those sharding to the result tensor. For example, if you shard your input tensor and then you do a bunch of operation, like all of the operation in between should also be sharded, and the result is most likely also sharded. So let's do SPMD. So in order to use GSPMD, we need to introduce two concepts, mesh and the partition spec. So I will quickly go over here. I will show you more graph and Colab, so don't worry if this concept doesn't really make sense right now. So mesh represents the device topology, and the product of mesh shape is the total number of devices. What does it mean? So if you look at this example here, we are constructing a 2D mesh. So like the mesh shape is 2D. So the first dimension is the number of devices, assuming we're on a TPU v8, so there will be 4 devices. So the mesh shape is 4 by 1. And we also name the dimension of first dimension to be the data and the second dimension to be the model. So this is kind of just dummy code of initializing a mesh. Let's see like how it's going to take effect very quickly. So partition spec, on the other hand, so mesh describe the device topology. So a partition spec, it describes how a mesh is being mapped to the tensor. So for example, if you remember our mesh, so it has 2 dimensions. The first dimension is called data, second dimension is called model, and data is 4. Well, data is num device. In our case, let's assume it's 4 and model is 1. So a partition spec pretty much means how will the mesh be mapped to the tensor. For example, in this case, you have a tensor that's 8 by 4. So the partition spec means the first dimension, which is 8, will be mapped to the mesh dimension data, which has 4. So which means that we want to shard the first tensor 4 ways. So let's say V4A, 4 device, so each device will get a tensor 2 by 4. And the second dimension is mapped to the model, which model only have 1. So pretty much means the second dimension is being replicated. That's probably a bit vague on like what does it mean. So let's take some graph. So this is kind of conceptually what it is. On the left, that we have all of the device, mesh describe the device, and then partition spec is something that is sitting in between of a mesh and a tensor, and partition spec describe how a mesh is being mapped to a tensor. So let's take our original example. So the mesh is 4 by 1 because you see we have 4 devices, and the data dimension is 4 and the model dimension is 1. Partition spec says data dimension is mapped to the 0th dimension of the tensor. The tensor is a 4D tensor. Let's say it's like 4 by 4. And the model dimension is mapped to the second dimension of the tensor. So in this case, we want to shard the first dimension by 4, which is what we do here. Let's say we flip the partition spec, say it's model data. Then now, like we didn't shard, we replicate the 0th dimension because the model dimension is 1. And then we shard the second dimension by data dimension, which is by 4. You can also have a mesh that's 2 by 2. So in this case, we will shard both the first dimension and second dimension by half. You also don't need to have a 2D mesh, like you can just have a 1D mesh saying, well, that's only one dimension, which is called data. In this case, we can still shard the first dimension of the tensor, and second dimension we put none. None pretty much just means we are going to replicate. So that's one concept here. So partition stack always have the same rank as a tensor, and the content of the partition stack is what we get from the mesh. So I think that's my last slide. Let's go over a Colab example. So it's more clear. I will also post this Colab and my slides in the video description. So first thing you need to do is that you want to change your runtime type to the TPU v2, which is already the case. Okay. So let's see what we do here. So just on licensity import, we import Torch, Torch XLA. They are both installed on the Colab if you choose the TPU v2 runtime. So we also import the X-ray model, the Torch X-ray distributed SPMD as XS. So this is what we're going to use a lot. The runtime is XR, like you know what we need it very quickly. So the version I'm using is 2.3. But by the time you watch this video, it might already be updated to 2.4. But 2.4 release will be out in a month or so. So first thing we need to do is call xr.use SPMD. So pretty much like this is telling the Torch X-ray that I want to run in the SPMD mode. So for now, let's don't go into too much detail, but pretty much it means like in the current process, the PyTorch X-ray will grab all of the runtime device. Like in our case, it's a TPU v28, I believe, on the Colab. So the current process will grab all of the 8 process. But that's what happened under the hood. If you're trying to query the device, like for the most part, Torch X-ray will tell you that's only one device. So that's a core idea of the SPMD. Don't think about how many physical device there is. When you're writing your model code, they're just assuming that's one giant device. And then you do the distributed by just annotating some of the tensor and tell the X-ray compiler how to shard them. So this is the same code that I have like in my presentation. For more detail, you can also just go to PyTorch X-ray GitHub repo in the docs. There are a couple of the SPMD docs. Like this example, pretty much I copy from the SPMD basic. So we are creating a 2D mesh. So the 0 dimension is called data and second dimension is called model. And then the data dimension has like 8 devices, and the model dimension it's 1. So if you print a mesh access name, it tells you it's data and model, and mesh shape is 8 by 1. So that's like wherever partition spec, that's when you shard that model, will shard that dimension 8 ways. So now let's initializing the tensor. So let's use torch.random. So we randomly initialize the 8 by 4 tensor, and then we move it to the X-ray device. So that's a T X-ray. So what we do here, so we initialize the partition spec as data and model. Remember, so in here, data is 8 and model is 1. And then we call the mark sharding. This is the core API you want to use, which this is the API that takes the tensor, mesh, and partition spec. And then you will apply the sharding to the tensor. This is an in-place op. So just by calling this mark sharding on the T X-ray is already sharded. But then you're also going to return your X-ray sharded tensor, which will have more like information about how this tensor is being sharded. So let's say we execute this. Yeah, actually execute. Let's just quickly execute all of this. Okay, here we go. So it will tell you the xt, which is like X-ray sharded tensor, and local shards, which is the actual shards in the physical device. It will tell you there are 8 of them, which makes sense because we shard the data 8 ways. And if you print the local shards 0, for example, like this is a 0, this is 1 by 4 tensor. Remember, like our original tensor is 8 by 4, but we shard at 0's dimension 8 ways, which is data dimension. So each device actually holds a 0 by 4 tensor. Actually, if we print it's probably more clear if we just print the original TCPU, and then you see. So you see the 0's dimension is actually what is in a local shard 0. And the second dimension map to like the second item like in the local shot and tell you like the first shot was in the TPU 0, second shot was in TPU 1. There are 8 TPU in a collab. Each of them also have 16 gig HBM, I believe. So this is just like quickly tell you. So T-X-ray, which is here. So we move the CPU tensor to X-ray tensor. The type of it is still a torch tensor, but if you print its device, it's going to tell you it's X-ray. T-X-ray dot device. Yeah, it's in X-ray 0. And XT, which is torch X-ray dot distributed SPMD X-ray shorty tensor. For the most part, you don't need the XT. Unless you're trying to print some debug info about the shorty tensor. You can just call a mock shorting without this equal statement, and then T is already being shorted. And then we can just do a quickly all cross to verify like the result is the same. So you might wonder, now we short the tensor, now like this T-X-ray actually resides like in 8 devices. What's going to happen when we call .cpu? Well, what's actually going to happen is that before we moving the T-X-ray back to the CPU device, we actually performing all gather, and then we concatenate the tensor, and then we pass it back. So from user perspective, you actually don't need to worry about it. For the most part, you can think of it as just one giant device. After you shot the tensor, then all of the collective happen implicitly. When you want a result, you can just move it back to the CPU. So now let's actually run a slightly more complicated example. Let's try to run ResNet 18. So we get the ResNet 18 from the torch vision, and then we just have a simple input, a batch channel dimension, and let's say the batch is 512. And the channel is 3. I think it's pretty standard. So now, like, how do you use it? How do you use SPMD in a real-world model? Well, there are many ways to use it, but in this case, let's pick the easiest one, which is, let's say we want to do data parallel. So what is data parallel? Data parallel means like the model parameter actually resides on all of the device. So like there's a copy of a ResNet 18 parameter on all 8 TPU device, but each of them was handling different part of the data. So the data is 512. And then 512 divided by 8, I believe 64. Yes, 64. So we want each device to handle the 64 out of this 512. How do we do? Remember, we still have a mesh. The mesh is 8 by 1, and then data is 8. So we want to short the input tensor, and we give it a mesh, which is 8 by 1. And then we say we want to short the first dimension, which is the batch dimension, by data dimension, which is 8. And then we just do a normal computation. We pass the input to the model, and then we call a mock step, which pretty much it means that let's just execute this graph. Otherwise, when you just run a model with PyTorch XLA, it's only going to tracing a graph, but it does not execute. And then you just print a loss. Everything works as expected. Like there are more fancy way to short. For example, like you can short a model parameter. If you short at 0th dimension of every model parameter, which is pretty much FSDP. I will go over that in a follow-up video. But for today's purpose, this is what it is. So this is SPMD and how to use it with PyTorch XLA. Again, I will attach all of the code and slide I use in the video description. Please leave a comment or open a GitHub issue if you have any questions or comments. Thanks.